One of the things that I have always wanted or requested flat earthers to do is to try to combine what we know about physics with what they are telling us. Now, one of the things that flat earthers will always tell us, or usually tell us, is that they are trying to replace gravity as we know it with density and buoyancy. And since I've been asking flat earthers for so long to show us how they are actually going to do that, I thought to myself, why not try to do it myself and help them out a little bit. So let's do that in this video. Hello and welcome back to my channel. As always, I'm Michael. And today we're going to look at one of the biggest flat earth mantras, especially if you ask one of the bigger flat earthers, Eric Dubai. One of the things that he usually tells us is that there's no gravity, there's only buoyancy and density. But as we all know, in order to have motion, we also need to have a force. More specifically, in order to have acceleration, we need to have a force. Now, as I will show in this video here, as you probably can guess, so one of the biggest flat earth mantras that I have used, one of the bigger flat earth one of the bigger flat earth mantras that I have heard again and again and again, especially from someone like Eric Dubai, is the continuous attempt to try to replace gravity as we know it with density and buoyancy. Now, one of the things that I have asked flat earthers for so long to do is to give us some form of calculation, some form of formula that we can use to try to predict these things, that we can use to show how density and buoyancy can actually replace gravity on the Earth. Spoiler alert, it can't. But I've asked it again and again and again, like I said, and usually I've been met with this sound here. Yeah. So I thought to myself, hey, why not try to do it myself? First, cup of coffee. Cheers. I will preface this video here with by showing I will preface this video here by first showing you how we can derive the gravitational constant little g. It's not really the gravitational constant, it's the gravitational acceleration on Earth, but how we can derive it on our normal spherical true Earth, as I would like to say, because the universal law of gravitation is a little bit cumbersome to use. It's not terrible hard, but it is a little bit clumsy. So we wanted to reduce it as much as we can, and I'll preface this video, like I said, by showing you how we're going to do that. So let's go over to my slides over here and let's take a look. So as you can see here, we're finding G on a flat Earth. So first we're going to look at G on the real Earth. I mean, the spherical Earth that we all know it is. Let's try to look at that. So we all know that the universal law of gravity that Newton gave us, which by the way is still true. In this context, let me try to make something very clear here. So while it is true that what some flat earthers say, that Newton's explanation of gravity is rejected and it is Einstein's general relativity that is the true one, while that is true, it means that it's only the explanation that Newton gave us, you know, the ones with forces between two objects and all of that. It's only the explanation that Einstein rejected. The law in itself, the universal law of gravity, is still applicable in some circumstances, as we know that the universal law of gravity that Newton gave us can be used on most of the solar system. But when we get near to very strong gravitational fields, for instance the Sun and Mercury, then the law that Newton gave us begins to break down and we have to apply Einstein's field equations instead, which is also one of the tests that Einstein suggested himself to look at the orbit of Mercury that Newton's law cannot explain, but Einstein's general relativity can explain. But to say that Newton's work is completely dismissed is false. For one and very particular good reason. One of the objectives or goals that Einstein had was that his work, his field equations, had to be invariant with Newton's law of gravity, his universal law of gravity, meaning that if you reduce Einstein's field equations to a scenario comparable to the Earth, then you would end up with the laws that Newton gave us. But we have it here. We have the Newtonian law of gravity right here. And let's discuss a little bit what it says, because it's fairly easy to explain. We have two masses, m1 and m2. We have forces between them. Now again, this is Newton's explanation, but in order to explain how this law actually works, I think this is a fairly good figure to use, even though it strictly speaking is wrong. So what does the law that Newton gave us say? Well, it says that the F1 force, the blue ball, towards the M2 force, and the M2 force towards the M1 ball, they are both equal to each other, but they're also equal to big G, the gravitational constant, times M1 times M2 divided by the distance squared. So M1 and M2 are the two masses. So let's try to calculate using an example exactly how this works. So as you can see here, we have the law up here, Fg equals G M1 M2 divided by R squared. So as I said, it's a long and annoying to use. It's a little bit cumbersome. So let's take an example. Let's say the Earth radius is approximately 7,000 kilometers. And we can also say that altitudes near Earth are much smaller than our Earth. So for example, if I take a bowling ball and lift it up 20 meters on a ladder, something like that, the altitude that I've gained, the 20 meters, is insignificant compared to the radius of the Earth. We have the correct values down here. Our Earth is 6.378 times 10 to the 6 meters. G, the gravitational constant, is 6.674 times 10 to the minus 11th Newton times meter squared divided by kilogram squared. And then we have the mass of Earth, which is 5.972 times 10 to the 24th kilograms. And yes, I'm using kilograms. I am not using the horrible and forever imperial system. Sorry, both Brits and Americans, but I really hate that freaking system. It's... well, let's continue. Like I said, we are trying to calculate the force on a 10 kilogram bowling ball at, let's say, 20 meters altitude. That's one of my numbers that I selected. We already have the mass of Earth, we have the radius of Earth, we have the mass of the ball, that's 10 kilogram, and we have big G, so the gravitational constant. In order to find the radius, when I say radius, I mean R squared, because it's not really a radius, it's a distance plus a radius. But in any case, R in this case here is a radius of Earth. I don't know why I made that with big. Well, in any case, radius of Earth plus the height of the ball. So it's 6.378 times 10 to the 6 meters plus 20 meters, which gives us 6.37802. Yeah, times 10 to the 6 meters. So it's a very minute little change, which is also going to show up in the calculations. So already now from this number here, let's just make a quick assumption. So we're going to step a little bit ahead of ourselves here. And we are going to actually sort of just roughly calculate what the force on this ball here would be using the ordinary F equals mg that we sometimes use. Now, in most instances, we would say that G is equal to 9.8 meter per second squared. It's the gravitational acceleration. And in this case here, we could say, well, we have 10 kilograms times 9.8, which gives us 98. So that's roughly what we're going to get. And spoiler alert, this is also what we're going to get with this formula here. So let's continue. So like I said, we put in the numbers. So we get 6.674 times 10 to the minus 11th Newton meters squared per kilogram squared times 5.972 times 10 to the 24th kilogram times 10 kilograms, that's M1 and M2, divided by 6.37802 times 10 to the 6 meters squared, giving us 98 Newton, like I said. So in order to reduce this to something a little bit manageable and something that works in the general vicinity of Earth, we're going to make some assumptions. One of the assumptions that we're going to make is that the height, in this case here, the 20 meters, is insignificant compared with the radius of the Earth. So basically, no matter where I am in the vicinity of Earth, as long as I'm not up too high, then the radius of the Earth is basically the same all the way around. So we will try to reduce the equation then. So we see that M Earth, R Earth, and G as constants, and we will collectively call them G. So again, we put in the gravitational, the universal law of gravity. Fg equals big G times M1, M2 divided by I squared. So we pull all of that up, we call the constants. In this case here, I'm calling M2 the mass of the Earth. R is obviously the radius of the Earth, and we already know what G is. So we get M1 times GM2 divided by R squared. So all of that over there on the right hand side, we reduce to G, so we get Fg equals Mg. So in order to really sort of ascertain this, we need to also be assured that all of these constants, we call them, that we sort of lumped together on the right side, that they actually give us what we need. So we try to calculate this number here. So we put in all the numbers that we have before. 6.674 times 10 to the minus 11th Newton meter squared divided by kilogram squared times 5.972 times 10 to the 24th kilograms divided by 6 times 6.378 times 10 to the 6 meters squared, giving us 9.8 Newton per kilogram, where, and this is important actually, Newton per kilogram is the same as acceleration. So we get, in fact, 9.8 meters per second squared. Now, this is one of the things that I find particularly interesting by some of the complaints that flat earthers always give us, is that this number here derived, this is completely theoretical derived. I mean, yeah, sure, we got the numbers for the radius of the Earth, the mass of the Earth, and we got the gravitational constant. But other than that, everything else is completely theoretical. I have not been out measuring anything sort of in reality other than the masses and all that. And let's say we could even derive those. We didn't need to measure them in any way. So I think this is an interesting thing. And I will bet you that if I put in the numbers for where I live, roughly, and compare them with the numbers that I already, I did this experiment, I did it at university, and I've done it here at home. It's very simple. You download a little program. In my case, I think it's called SensorLog for iPhone, but I'm pretty sure that you can get something equivalent for Android or whatever you have. And inside your phone, you actually have an array of very, very sensitive sensors. They're called accelerometers. So your phone is actually calibrated to a certain gravitational constant. I believe in the case with SensorLog, as far as I remember, it's 9.80 meters per second squared it's calibrated to. The measurements in themselves is actually fairly easy. You pick out some really good pillows or something very soft and something that can break the fall from the phone. And yet you just hold it up in a certain altitude, enough that the phone can accelerate a certain point. And then you just drop it. And you do that a couple of times, and then you get some measurements. And one of the interesting things that I found was that I could actually see a difference when I dropped the phone flat, so that it had a lot of wind resistance compared with if I dropped it on the side. So it would actually accelerate faster, a little bit faster, on the side than it would on the other side because of the wind resistance. That really goes to show how sensitive these instruments really are. And just as I expected in that little experiment, what it gave me was pretty much the number that we got here. I think it was 9.81 or something like that, which is consistent with what I would expect here at my latitude here in Denmark. So yeah, there you have it. at least you could say that no matter what you, as a flat earther, think about gravity, if you think it's real or if you think it's fake or whatever you think, at least you have to recognize that the theoretical number that I derived right here on the screen is fairly consistent with what we can measure in real life. So here comes the thing, right? I thought, well, I would really like for flat earthers to try to derive this number here. I did that on one of the Danish flat earth sites that on Facebook that I've been kicked out from because I'm apparently not flat earthy enough, I guess. Well, that's the way it goes, I guess. But meanwhile, I asked around, asked them, well, why don't you try to derive this number here? And I got all kinds of different answers with, well, math is fake and it cannot be used for anything and there's no real connection between math and the real world. You know, all the usual flat earth excuses for actually doing some real scientific work. We also had a discussion about errors in measurement and all of that, which flat earthers also seem to completely be careless about. They don't, some of them even don't know what it is to take care of any errors you might have in your measurements. But in any case, let's go ahead and try to derive this equation here on a flat earth. So let's go back to the slides. All right, so here we are, G on the flat earth. Let's try that for a second. So, like I said, flat earthers, they love to use the density and buoyancy explanation for whatever reason. I'll say I do think I have an idea why they are so much in love with this particular explanation here, especially density, but I'll get back to that later on. So I thought, well, let's derive G in this context and let's set the stage for this. So Newton's second law of motion, F equals ma, is, using the ever-going flat earth mantra, demonstrable, repeatable, and provable true. So, any motion on Earth has to adhere to this law. That's a fact. Particularly its acceleration that needs to adhere to this law. This also means that F equals mg has to be true in some context on flat Earth, because g in this case here is just another word, another expression of acceleration. We also know, because this is something that I've measured myself, like I said, that any flat earther can measure themselves, we also know that any object in freefall motion accelerates with roughly 9.8 meters per second squared, depending on your latitude. This is also demonstrable, repeatable, and provable. As I've written probable, it should say provable true, not probable. It's provable. We know that density is defined as rho equals mass per volume. So that's basically that's density. And we also know that buoyancy is defined as F, the buoyancy force, is We also know that density is defined as rho equals m divided by v, where v is the volume. And we know that buoyancy is defined as F buoyancy is equal to minus rho g volume. Ergo, we do need g in order to continue here. As this little figure I've put in down in the bottom here, we have the buoyancy force, which basically is an upward force. And then flat earthers, I would suppose, is trying to replace the weight here with the downward force. So let's continue with that. That's at least as I, as a physicist, would see these things. So let's continue. So we know that in this case here, the density probably wouldn't be the acceleration in that sense, because it's the acceleration that we need. I would say that the force in this case here has to be density. So we are replacing the downward force with density. This means that we know that this downward force also needs to be m divided by v, mass divided by volume. We can then rearrange F equals ma to get F equals ma, F divided by m equals to a, then we get a equals to force divided by mass. This is also true because, like I said, it's demonstrable, repeatable, and provable, or whatever they say. We now reduce this expression further by inserting F equals m divided by volume, mass divided by volume, m divided by v, to get a equals to m divided by v times 1 over m. That is, a is equal, the acceleration is equal to mass divided by volumes times mass. Basically saying that on a flat Earth, the gravitational acceleration, a in this case here, but g, is the volume. Now, I am not going to say that I am a particularly big expert on the flat Earth. I mean, I obviously is not. But I'm pretty sure that even on a flat Earth, the gravitational acceleration does not equals or change with the volume of something. The mass, perhaps, I could see that, but not the volume. I mean, this is... yeah, you can see it for yourself. It's meaningless. Basically, what we're saying is that G is equal to volume on a flat Earth. That means that F equals mg is F equals m volume. Nah. Also, again, we need to have 9.8 meters per second squared. Now, volume is not an acceleration by any means at all. Furthermore, this means that any acceleration we have, any free fall we would have on a flat Earth, would only work with something that is precisely has a precise volume of 9.8, which is ludicrous. I mean, even the units, right? Volume is liters or cubic meters. It's not an acceleration. So again, we're stuck. Let's continue, because we had the buoyancy before, and we need to look at that. And when we use buoyancy, it becomes even more crazy. So let's continue. So yeah, like I said, we're going to further derive the new expression for buoyancy. So as we said before, force buoyancy is equal to, well, I forgot the minus sign, but let's let that one slide in this case here. So force buoyancy is equal to minus rho g v. Now again, we just found out that G in this case here is equal to V, the volume. So we get the buoyancy force is equal to rho V times V, basically saying that the buoyancy force now is rho times volume squared. I am pretty sure that if a flat earther, if you take any kind of balloon, it can be a hot air balloon, it can be a helium balloon, I'm pretty sure that you won't find that the buoyancy force scales with rho times the volume squared at all, in any case. So this is what I got. What I'm trying to say with this here is that this is the kind of work that I am looking for in you flat earthers, that I want you to do. Now, I'm not saying that this is true. Obviously, this is nonsense. It's I mean, mathematically it's okay, and physically, I mean, it's technically a correct derivation, but any person with just a slight knowledge of physics would say that this is completely ludicrous. It has nothing to do with the real world at all. So like I said, what I want you to do, flat earthers, is I want you to derive this expression here for yourself. This was meant to be some kind of incentive or inspiration for you to get the ball rolling. But I'm pretty sure that no matter how you want to structure these formulas here, you'll end up in a place where this doesn't make any sense. So basically what I would say that we can derive from this little exercise here is that buoyancy and density, in this case here, particularly density, has absolutely nothing to do, cannot replace the force of gravity. Now, I promised you in the start of this video that I will try to give you some form of explanation as to why I think that flat Earth has chosen particularly density as opposed to something completely different. And I think that the idea here is that for many people there still is some form of idea that if you have a very light object and you have a very dense object and you drop them, they will fall with different speeds. They won't, they'll accelerate with the same acceleration, but there's still this idea that the more massive or the more dense an object is, the faster it will fall. It won't, but there's still this idea. Mainly because people have some form of idea that when they think of dense object versus light objects, for example, if you have a bag of feathers and you have a bowling ball and you drop them, they will most definitely fall at different speeds, different rates. But that is because there's more wind resistant working on the feathers. There's more of an effect on the feathers that it will have on the bowling ball. But if you compact the feathers down to a very tight little bag, there's as little air inside the bag as possible, and the bowling ball and the bag of feathers, now still weighed roughly the same, they will fall at a more equal rate. The other thing is that since there is a connection truly between the force from gravity and the mass of an object, and mass is related to density, I guess I can see why they chosen density as in this case here, because, well, as you can see yourself, if you have a more dense object, let's for example say that if you fill a suitcase with pencils and you fill a suitcase with blocks of lead, there's no denying that the suitcase with lead will weigh more than the suitcase with pencils, because for one, the density of lead is very much higher than the density of pencils. But it still, I will say, comes down to a very wrong understanding on how physics works, because we have shown again and again in physics that if you take objects with different densities but roughly the same size, for example some balls that have the same size but different densities, meaning that the wind resistance will be roughly the same on all of them, and you drop them at the same time, they will also land roughly at the same time. There can be minor variances in this case here, but in general they will fall at the same rate. Alright, that was all for me in this time here. I think it was long overdue that I made another flat earth video, because I had some new content to go on. Now I will continually try to find some good new inspirations to again go on the train and try to debunk flat earthers, because honestly, despite that it has taken me a very long time to make another video, I actually do find it pretty fun to do. So see you around in the next video, and stay safe out there. Bye bye.